trying to understand what is accommodation right from the basics. A normal eye which does not have any refractive error can look at far and can look at near objects quite easily and clearly. To understand accommodation, let's try to understand the total power and the refractive power of the eyeball. As I already told you in the anatomy of cornea that the major refractive surface is the cornea because it has the major power in the eye about plus 45 diopters. And the next refracting surface is our crystalline lens, and the lens has about plus 15 diopters of power. So these two together will actually form the total power of the eyeball, that is 45 diopters which is coming from the cornea and 15 diopters which is coming from the lens. So it comes to about plus 60 diopter power. And since the power of the eyeball is in plus, it means that the eyeball acts as a converging lens, and the rays of light which are coming from far, usually they are parallel rays of light. So when such parallel rays of light will pass through the cornea and through the crystalline lens, which are the major refracting surface, and pass through the eyeball which has the converging capability, these two rays of light will actually converge and focus on the retina. So remember that parallel rays of light will always come from far and from the infinity. However, whenever we are looking at a closed object, that means an object which is located very near to our eyeball, what happens is that the rays which are coming from that object now will be diverging in nature. Okay, so the rays which are coming from far will be parallel. However, the rays which are coming from a near object will be diverging in nature, and the eyeball will now not be able to converge with that power of plus 60 diopters enough to bring the focus on the retina. So what is happening with this limited plus 60 diopter, the average power of the eyeball can actually converge only the parallel rays of light which are coming from far onto the retina. But whenever an object is placed near to the eyeball and we have to look at the near object, the rays, instead of being parallel, they will be diverging in nature, and such diverging nature of the rays will make them focus behind the eyeball. As the eyeball with its plus 60 diopter power was not able to converge the rays which are coming from the near object, which are diverging rays, onto the retina, there is a need to increase the convergence power of the eyeball, especially when we are trying to look at the near objects. And this is actually accomplished by increasing the refractive power of the crystalline lens. And how do we increase the refractive power of the crystalline lens? By increasing the curvature of its anterior surface. And this process, in which we increase the curvature of the anterior surface of the lens so that it becomes more fat and it develops more refractive power, so that the convergence power of the eyeball increases and the rays will now focus onto the retina. This entire process is called accommodation, because the eyeball, and to tell you the lens in particular, is trying to accommodate for our need to look at a near object. So this is what happens. Once there is accommodation, that means the lens will now become fatter. The lens will increase its the lens will actually become fatter and increase its converging ability. So what happens now? The rays of light which are coming from near, which were diverging and initially getting focused behind the retina, now because of the increase in the convexity of the anterior surface of the lens, will now have increased power of the lens, and therefore now they will be able to focus onto the retina, right? And this process is called accommodation. So what happens normally, if this is considered to be our normal eye, in which you can see the rays are parallel because this is an unaccommodated state, that means the patient is looking at far. So whenever we are looking at far in the unaccommodated state, our lens is spherical in such a way that the radius of curvature of the anterior surface is about 10 millimeter and the radius of curvature of the posterior surface is about 6 millimeters. In order to look at the near objects, like looking at the fine prints of a textbook or newspaper, the eye will actually undergo again the process of accommodation. And what did I tell you? In the accommodation, it is the anterior surface of the lens which will become more convex. So as the lens will become more convex, the radius of curvature will now change from 10 millimeters to about 6 millimeters. However, it is only the anterior surface of the lens which will undergo change in the radius of curvature, and the posterior curvature of the lens will remain the same, that is 6 millimeter in the normal unaccommodated state, and even in the accommodated state the posterior surface of the lens will remain same. So before I tell you how does accommodation takes place, it's very important for us to know the basic anatomy of the lens. So this is the lens, and we know that the lens is situated behind the iris, okay, and then behind the iris we have our ciliary body. Okay, the ciliary body consists of an important muscle which is called the ciliary muscle. Now the ciliary body is connected to the equator, that is the ends of the lens, using certain fine fiber-like structures, and these fine fiber-like structures are called the suspensory ligaments of the lens. The ciliary body is thrown into folds, and these folds are called the ciliary processes. So from the ciliary processes we can see certain ligaments which are present, and these ligaments are present on both the sides, and they will actually suspend the lens from the ciliary body. Now since they're suspending the lens from the ciliary body, they are called the suspensory ligament of the lens. Now let us try to understand the mechanism of accommodation. So in accommodation, whenever we want to look at a near object, what happens is that there will be contraction of the ciliary muscle, right? So this is the cross section of the eyeball, and as I told you that in the eye we have the lens, and the lens is actually suspended with the suspensory ligaments of the suspensory ligaments, and these suspensory ligaments will be connecting the lens with the ciliary body, and in the ciliary body we have an important muscle which is called a ciliary muscle. Now whenever a person is looking at far, the rays are coming parallelly from the infinity, and at that time we do not need accommodation. So at that time the ciliary muscle is in a relaxed state. Okay, so when the ciliary muscle is in the relaxed state, the suspensory ligaments are actually very tight and taut. Okay, so as they are tight and taut, the lens is also in its normal shape, which is a flattened shape. Now, however, when we look at a near object, there is a need for accommodation, and the ciliary muscle will recognize that need and it will undergo contraction. As the ciliary muscle will contract, this band of ciliary body will actually increase in its width. Okay, so you can compare the width in the first image from the second image. The width is more. Now, as the ciliary muscle contracts, the width of the ciliary band will increase. So what happens to the ligaments? What happens to the space here? This space will get narrowed, and therefore the suspensory ligament will now become more loose. Okay, because the suspensory ligaments during the accommodation, because of contraction of the ciliary muscle, will now become loose or lax. Okay, so now as they become loose or lax, their hold on the lens will also become loose, right? So now the lens becomes more free to move in its own way. Now the lens structure and the lens capsule is very elastic. So as the tautness and the tightness from the suspensory ligaments is lost during accommodation, and as the laxity comes, the lens will now be free to actually move forward. Okay, the lens will actually move forward, and at the same time the capsule of the anterior part of the lens also will move forward, and all the lens matter will also move forward in such a way that the anterior convexity of the lens will increase, and the lens will now become globular. Now as the lens becomes globular, we know that the convexity will increase, and as the lens convexity increases, the converging power will increase, and thereby the lens will now be able to focus the diverging rays onto the retina. So this is the process of accommodation, in which the ciliary muscle is very, very important. Now, After we know what is accommodation, there are two important points that we should know. Number one is the near point of accommodation, which is called the punctum proximum, and the number two is the far point of the eye, which is also called the punctum remotum. The nearest point is nothing but it is a point at which the small objects can be accurately focused by the eye. Okay, it's the nearest point at which the small object can be accurately focused. Right? So this nearest point is different according to the age. In a child, since the accommodation is very active, the near point will be very close to the face, about 7 mm also, 7 centimeters, sorry. But as we age, the ciliary muscle will get weakened. The elasticity of the lens will decrease because of the nuclear sclerosis and cataract development. The elasticity of the lens capsule will also decrease. Therefore, the accommodation will decrease with age, and people actually get accommodative defects and accommodative refractive errors like presbyopia. Right? So what happens in old age is that the near point of accommodation will actually recede or become more as the patient will age. Right? So near point of accommodation is not same for every person. It will vary according to the age of the person and according to the accommodation facility of the person. Coming to the far point of the eye, the farthest that a person can see is the far point of the eye, or the punctum remotum. Now again, the far point of the eye will vary according to the refractive status of the person. An emmetropic person, that means a normal person, will be able to see at infinity. So the far point is at infinity. However, in a case of a myopic patient, the far point will be actually in front of the retina, and in case of a hypermetropic patient, it will be behind the retina. So in both these cases, the far point will not be at infinity. So again, I will repeat that the near point will vary in a patient based upon the age, and the far point will vary based upon the refractive error of the person. So let us see what is meant by range of accommodation. The difference between the far point of the person and the near point of the person is called as the range of accommodation. Now over here, I want to add a clinical point, that how do we measure the near point of accommodation and the far point of accommodation? It is actually done using an instrument which is called the RAF rule. Okay, so the RAF rule stands for the Royal Air Force rule. Okay, so it's an instrument which can be used to measure the far point and the near point of accommodation, and if you have those 2 points, you can subtract them and find out what is the range of accommodation. Let us see how do we calculate the amplitude of accommodation. The amplitude of accommodation is actually measured in the units of diopters. Okay, number one. Second, it is nothing but it is the difference between the refractive power of the eye when it is accommodated, that means when it is looking at near, minus the refractive power of the eye when it is not accommodating, that means when the patient is looking at the far distance. And how do we calculate power? Power in diopters is the reciprocal of the near point or the far point in meters. Okay, so whether it is near point or it is far point, you have to take it in meters. So usually the near and the far points will be in centimeters. We have to convert it into meters and then calculate the reciprocal of that, and that will give us the power of the eyeball in that state. So AA, that is the accommodative amplitude, is equal to refractive power of the eye when it is accommodating. So that is nothing but 1 by near point of the eye in meters, minus the refractive power of the eye at rest, that is 1 by far point in meters, because at rest means the eye is not accommodating. And when is the eye not accommodating? When the patient is looking at far. So now in this table, it shows that as the patient age is increasing, we can see that the near point is also increasing. At the age of 5, it is very close to the face at 5 centimeters. Why? Because the amplitude is also more, right? And you can see, look here, the amplitude of accommodation. Since the amplitude of accommodation is actually decreasing with age, the near point is actually increasing with age, right? So because the amplitude of accommodation is nothing but the power of accommodation of an eye, and as you can see, a patient who is 75 years of age almost the amplitude of accommodation is 0, and therefore the patient will definitely need some correction to look at the near objects. They do not have accommodation at all. However, a child who is about 10 years of age, his near point is about 8 centimeters and his amplitude of accommodation is 12.5. Right? So important point that as the age increases, amplitude will decrease, amplitude of accommodation will decrease, and therefore the near point will increase or recede. Now let us calculate this amplitude of accommodation with some examples. In the first example, we will take a child who is about 10 years of age and who is emetropic. Okay. So first, what do we need is the near point of accommodation for a 10 years old. For a 10 years old, it is about 8 centimeters. This is what we saw in this table. Now the refractive power in the accommodative state, that means at the near state. Okay. So what did I tell you? What is the near point? It is 8 centimeters. So the power will be calculated by 1 by 8 centimeters. We have to convert it into meters. So it will become 100 by 8. So the refractive power in accommodative state will be 12.5, and the refractive power of the eye of an emetropic eye will be 100 by infinity, because the patient can actually look at infinity, so it comes to 0, right? So what is the amplitude of accommodation? The first one minus the second, that is 12.5 diopters minus 0 diopters, so it comes to about 12.5 diopters. So this is the amount of accommodation that a person or a child of 10 years needs when he wants to look from infinity to his near point, that is about 8 centimeters. Now let us calculate the amplitude of accommodation for the same child, but who is actually myopic with 2 diopters of error. Now the near point of accommodation for the child will be about 8 centimeters. Okay. Now the refractive power in the accommodative state will be again calculated in the same way, 100 by near point, that is about 12.5 diopters. Now the refractive power, however, for the myopic eye, I'm so sorry for the typing error here. The refractive power for the myopic eye here is how much? It is about 2 diopters. So now if we subtract 12.5 from 2 diopters, we get 10.5 diopters. So if the child is myopic, he needs little bit less amount of accommodation compared to a child who is emetropic, okay, to see from infinity to the 8 centimeters distance. Now let us calculate the amplitude of accommodation for a hypermetropic child who has about 3 diopters error, okay, and the near point, say, in this child is about 12.5 centimeters. So as a near point is given, so already it's written here, and the refractive power in accommodative state will be 100 by 12.5, so it comes to about 8 diopters, and the refractive power of the, the refractive power here for the hypermetropic will be about minus 3 diopters. Now why we have taken it as minus 3 diopters is because if you take an eyeball and the image is actually formed in a hypermetrope behind the eyeball, right? So for the sign convention, it says that whenever the image is formed behind the eyeball, the refractive status has to be taken as minus, right? And when it is formed in front of the eyeball, as in the case of myopes, the refractive status will be taken as plus. Okay, for the usage in this formula, you have to consider the sign convention like this. So the refractive power for the hypermetropic patient, that is 3 diopters, because it's formed behind the eyeball, it will be taken as minus 3. So putting all these values in the formula, 8 diopters minus 3 diopters will come to 8 plus 3 diopters, that is about 11 diopters. So a hypermetropic patient, when he has to see from infinity to the near point, that is about 12.5 centimeters, as in this patient, he will need an accommodation of about 11 diopters. So I hope with these examples, calculation of amplitude of accommodation would be easier for you now. And now this graph is nothing but the Donder's curve. Okay, so this is called the Donder's curve. This curve actually shows that as the age of the patient is increasing, the amplitude of accommodation is gradually decreasing.